This video demonstrates some simple MATLAB code that can be used for prediction. The first chapter then, you'll notice, has had quite a large focus on open loop prediction, and the modelling part actually supported that. So viewers might find it convenient, that's the key word, to have some simple MATLAB code that they can use for finding these predictions and checking their own understanding. This video then gives an oversight of some code written by the author, which will be available on the same website as these videos. The code is written to be simple and straightforward so that somebody with a relatively elementary understanding of how to code in MATLAB will be able to follow what's going on and edit them themselves. Therefore, they're not designed to be optimized for computational efficiency or speed, and indeed that's hardly necessary these days, given prediction is relatively straightforward. First then, state space models. So here's the common discrete state space model that we've been using with model parameters A, B, C and D, and you'll notice down here we're going to assume that D equals 0. The output predictions given in an earlier video looks like this. You'll see we had a matrix P, a matrix H, and implicitly there was a matrix L multiplying upon the disturbance estimate. So what we're interested in is how do we find this matrix P, this matrix L, and this matrix H. Now, for completeness, you might actually want the predictions for the states, and these will be defined with a matrix PX and a matrix HX. So we'll give the code for finding those as well. Now, just as a note, the definitions of P and H are the same if you predict in terms of deviation variables, which clearly the earlier videos did. So again, what we're interested in is finding the same matrices P and H. So what we want is we want to find the matrices PH, L, PX and HX, and these depend on the model parameters A, B and C, and clearly the horizon that you're predicting to N. Now, what files have we provided? We've given a simple example file. That's the one that you should open if you go to the website to get it. Video 16 example 1, and you will see that inside that file, the key file doing the prediction is this one here, imgpc_predmat. Don't worry about why it's called that, there are historical reasons. And then you see you put in the matrices A, B, C, D, and the horizon that you're interested in, and the outputs are H, P and L. And in this file here there are a CISO and a MIMO example. So what we'll do now is we'll go to MATLAB and we'll just demonstrate this. So there's our MATLAB command window. If we just find, here's the file, you'll see video 16 example 1, and you'll see what we can do is enter some A, B, C, D matrices and a horizon. So we'll do that, and you'll see this is a CISO example with just one state to keep life easy. So if I put in that command there, which generates the prediction matrices, and you'll notice there they are. There's the H matrix for horizon of 5, P matrix for horizon of 5, L matrix for a horizon of 5. Now, if you wanted the state predictions, you'll notice you can use the same code, but what changes is what you put in for the C. So there, I'm going to do a different example which illustrates that better. What if I had a multivariable state space model? So here we go. I'm going to put in a multivariable system and change the horizon to 4. So there I've entered it, and here find my prediction matrices H, P and L. So you'll see now, because it's multivariable, L is actually blocks of the identity matrix. 4 blocks, because I said the horizon was 4. There's the P matrix, and there's the H matrix. And again, you'll see the H matrix comes in blocks of 2 by 2, because this was a 2 by 2 system. Now, if you wanted the state predictions, you change the statement. If I go across, you'll see the key change in the statement here is where you had the C, I now put identity 3 because there's a 3 states. So essentially I'm treating the states as the outputs, and then that sends out the HX and the PX matrices that you might want. What if you've got a Karima model then? Well, a Karima model, given as AY equals BU, or what we tended to do was multiply it by the integrator, so we got capital AY equals B delta U, where capital A was A times delta, and we wrote these out in this form. And what we said is you can form explicit expressions for the predictions like this. You'll see CA inverse CB, where CA was a Toeplitz matrix, and that gives you essentially the H, a CA inverse times HP, and a CA inverse times HA. So you can get a more compact form. Call the first matrix H, the second matrix P, and the third matrix Q. Those names are obviously arbitrary, but what we're really interested in is getting H, P, and Q. Those are the prediction matrices. So we want H, P, and Q, and these depend on the model parameters A of Z, B of Z of our model, and the horizon N. The code's provided in a file, video 16 example 2, which is in the GPC folder, and in this case we've given two examples. We've given one which is called MPC Predmat, and we've given another which is called MPC Predmat Toeplitz. Now the difference is that the Predmat uses historical recursive methods to find the HP and Q matrices, so you might find the code a bit harder to follow, whereas the second example, the Toeplitz, uses the method that's been given in these videos, and we'll demonstrate that they both give the same result. Again, we'll give a CISO and a MIMO example. Okay, so we go to our code. So now we want the video 2 example, and we need to change folder because it's in a separate folder, that one there. So let's have a look at what we've got. We've got first an A, B, and an NY. Let's enter those. There they are, so A parameters, B parameters, and a horizon. And you see the first command, I can use this simple predmat command where I just put in A, B, and NY, and there's your H matrix, your P matrix, and your Q matrix. I could alternatively use this predmat Toeplitz one, and I've called them H1, P1, and Q1 just to differentiate, but what you can see is if I compare the results from those two pieces of code, the difference 10 to the minus 14, basically it's due to number errors on the computer, so it's insignificant. So you can use either method. The Toeplitz is easier to follow, but the Predmat uses historical recursive methods based on sort of Diophantine type identities, should you want it. What about a multivariable? Well, multivariable matrix faction description is a bit of a mess, but here's some code putting it in, and you can obviously look at that in the example 2 file if you want. So there's my A. If you look at it, my A matrix, A polynomial, B polynomial, and then I can put those in. So next then, let's look at our expression. We've got HPQ equals predmat ABNY. You'll see a very simple expression. We run it there, and then we can use the same basically the same requirement, but use the other file, the Toeplitz file, and again we can compare the difference between the two, and you'll see the difference is minimal. If you wanted to look at the matrices, there's H. Now obviously this is now very large. You might not want to look at this on the screen, because with a 3 by 3 system and even a small horizon, you'll see the H matrix gets very large, and you'll notice it's constructed of 3 by 3 blocks because it's a 3 by 3 system. And similarly, if you wanted, you could look at the P matrix and you could look at the Q matrix. So in the summary, it's common to use discrete models for prediction, and what we've done here is we've demonstrated some MATLAB code which you can use if you want to form unbiased n-step ahead predictions. The code is given for state space models and transfer function models, and most important thing is it's available on the website, which gives an overview of all these videos, so that'll be the Google's website.